Next speaker is Paolo Belardinelli from Università di Trento, and he's gonna talk about non-invasive closed-loop brain stimulation as a tool for research and rehabilitation. Thank you, Paolo.
Hi, thank you for your presentation. Okay, so my talk is about non-invasive closed-loop brain stimulation as a tool for research and neural rehabilitation. I hope I can convince you that this approach can be useful for both fields in an equal way. So just a little bit of an overview. In the first part, I will try to address the question why closed loop stimulation. In the second part of my talk, I will bring you two main evidences of the effectiveness of EEG state-dependent transcranial magnetic stimulation. And in the first part, I will briefly mention future perspectives for real-time brain network stimulation. This will be possibly in an hourglass fashion, going from general to particular, and then back to general with some kind of outzoom. So closed loop stimulation is basically a tale of two loops. So for several decades, the approach to brain stimulation was open loop. Basically, the brain was a black box. An input came in the form of stimulus, and we were inferring the results from the output. But there was basically no attention, no focus on the internal brain state. So then there is another kind of closed loop stimulation, which is when the stimulus is triggered by the brain state. So the brain determines the instant at which the stimulus is provided, and the output can vary depending on the brain state. And there is another kind of loop, the behavior in the loop, where the subject is interacting with the environment, and the environment is giving feedback to the brain. And this kind of so-called neurohaptic feedback is very well used in neural rehabilitation. In our case, it's like the brain is fluctuating in some kind of phase phase state space, and a stimulus, a TMS stimulus, depending on the initial state, is projecting the brain in another state and then another trajectory in time. And basically what we are measuring with EEG or non-invasive measures is a projection on the XY axis. So basically we are dealing with two loops, and I will delve deep into the brain dynamics loop. So why closed loop? To make a long story short, not only because there are now strong evidences that it works to some extent more effectively than open loop, but also because depending on the brain state, the effects of the same stimulation can have a different, radical different effect. For instance, this paper by he and others at cellular level shows that the presynaptic stimulation given in a time prior to the postsynaptic bursts turns into excitatory postsynaptic potentials, which are higher than non-state dependent stimulation. And the same stimulation given post the postsynaptic bursts turns out in long time depression with respect to the open loop stimulation. So depending on the mutual time with respect to the natural bursts, the effect, the long time effect on the brain can be opposite. So basically, what we thought at the level of non-invasive brain stimulation was to switch from TMS-EEG, that means giving a TMS stimulus and looking at the effect, at the transcranial effects by means of EEG, and go to EEG-TMS. That means observing the EEG state before the TMS stimulus and giving the stimulus on the basis of some kind of EEG measures. Because basically in the last few decades, the brain has always considered as a black box. We were looking at responses to TMS like muscular evoked potentials, MEPs, or transcranial evoked potentials, the so-called TEPs, the evoked potentials in the brain. But as a matter of fact, the brain state or the oscillatory activity at the time of the stimulation was never taken into account. So we thought of some kind of Copernican revolution, putting the brain back at the center of the system. And in the end, the idea about this kind of tailored and individualized brain stimulation and analysis was the following: that the EEG signals are fluctuating when a certain function of a certain unknown is met, that triggers the TMS stimulation, and this has an effect on the brain. This is conceptually a simple idea, but the implementation of this, the possibility of closing the loop in a brief time is not straightforward. So for our first experiments, we thought to focus on one local oscillation to close the loop on. And we found as most localized and clearly expected rhythm, the Rolandic mu alpha from the sensory end knob. This is one oscillation characterized by a clear rhythm, which is a little bit higher in frequency than the occipital alpha, and it's quite well localized. So the idea was to see what was the difference given the TMS pulses at peaks, at the positive peaks versus the negative peaks, the troughs of the mu alpha. And this has a physiological meaning, because for EEG, the negative peaks are basically the product of excitatory postsynaptic potentials of the haptic dendrites of the pyramidal neurons, whereas the positive peaks are coinciding and are a product of the inhibitory postsynaptic potentials. So the idea was that possibly stimulating at this time was producing more relevant effects than stimulating at this time. This is an original German paper, German book from some decades ago. The Mu rhythm from the somatosensory motor cortex is very well defined, and it should be noted, and we are working on it, that it's not exactly a sign. The oscillations are not symmetrical, whereas the power spectrum is very clear, and it's at about 10 Hz, oscillating plus minus 2 Hz, depending on the subject. And we were already corroborated in our effort from results from animal study, showing that mu alpha phase of local field potentials modulates firing rate in monkey sensory and motor cortex. So basically, the firing rate was higher in the troughs, in the negative peak of LFP. So basically, our closed loop setup, I'm trying to replicate in my new affiliation, is the following. So we have a procedure performed in the whole procedure performed in real time in about 2 milliseconds of temporal resolution. We have a trigger, which is the EEG rhythm obtained by a York filter around C3, around the C3 electrode. We have a TMS stimulus and some outcomes as the motor evoked potentials in the contralateral hand, and the transcranial evoked potentials as steps. But the real strength of the procedure is the short latency time. Then the pipeline is absolutely general. The trigger does not need to be an EEG signals or measure. The stimulus does not need to be TMS. It can be cognitive or whatever. And the outcome do not need to be MEPs or steps. So in our first experiment, the experimental hypotheses were that the instantaneous phase of local mu alpha oscillation in human motor cortex could determine modulation of corticospinal excitability. That means that basically the amplitude of the motor evoked potential after the stimulus, and the directionality of corticospinal plasticity. That means the amplitude of the MEPs long after a so-called intervention. So for excitability, we were expecting smaller MEPs for stimulus at the positive peak than the stimulus at the negative peak. And this is rather simple. So we expected the MEP signal to be larger or smaller depending on the mu alpha phase. But then we had a plasticity experiment where we measured the baseline with TMS and EMG. Then we had an open loop baseline. We had a closed loop intervention with triplets, which were state dependent. And then we measured several post sessions at 0, 15, and 30 minutes after the intervention to see if we could induce plasticity by means of this state-dependent approach. The experimental design comprised a lot of sessions, 1 excitability session, and 6 plasticity sessions. So 2 for C3 based positive peak, negative peak. Then we tried OZ to see if this was just a general effect or it was a local effect. We tried OZ peak, OZ peak, and OZ trough. And then we tried with 2 more plasticity sessions the mere temporal repetition of the C3 peak and C3 trough sequences to see if the mere temporal sequence can cause the effect. We had trials where the stimulus was effectively given, and the trials where only the trigger was marked in order to look for accuracy in our procedure. So the plasticity experiment was rather long. We had 2 baselines with TMS-EEG open loop, then a closed loop intervention, and 3 tests at different times after the intervention. This was the local YORT where we were basing our closed loop on, and this was the OZ YORT. It was interesting to see whether these 2 results correlated, that means a spreading of the activity, or anti-correlated, that means they were basically dependent but anti-correlated. So this was our theta bars-like plasticity inductive stimulation at peak, and this was our intervention for plasticity induction at trough, and this was out of phase. So we checked for several accuracy parameters. That we checked that effectively the Moore rhythm was coming from sensorimotor areas. We checked for our phase accuracy, and we checked that effectively on average we were always stimulating either peaks or troughs in the mu alpha way. So this is basically our main result for excitability. If the stimulation is given a trough, we have in the hand some kind of MEP rather large. If the stimulation is given the positive peak of the mu alpha, the MEP in the hand is generally smaller. And this is true for the average on the subject, but it's true in group average. And we have some results already that this kind of closed loop on alpha has different results on depressed subjects simulating dorsolateral prefrontal cortex with respect to the open loop approach. And moreover, dorsomedial prefrontal cortex closed loop stimulation modulates the working memory capacity of subjects. So it modulates behavior as well. So this was the main result for excitability. Corticospinal excitability is actually modulated by phase of local mu alpha oscillation. This is the group result. The difference is about 15%. It's not large, but the several things in the setup can be improved. What's important is that the MEPs at the positive peak were smaller than the MEPs at the negative peak for almost every subject, with the exception of 1. So these are the results for the plasticity. In the plasticity, we obtained a long-term potentiation for the intervention at trough, whereas we had a long time depression for the stimulation at peaks, even though this depression was not significantly different from open loop stimulation. The strong results we found is the potentiation for stimulation at troughs. Again, the effect is very strong for single subjects with 2 exceptions. And for the controls, we had no effect when triggering the OZ YORT, meaning that the phase-specific plasticity effect in the main experiment is due to the phase of local oscillations. So we were stimulating the motor cortex, but triggering the stimulation by means of the OZ oscillation, but no effect in this case. And no effect given the temporal repetition of the C3 sequence, showing that the direction of the induced plasticity depends really on the synchronization between stimulus and the brain state, and is not caused by temporal properties of repetitive TMS sequence.
Paolo, you have 5 more minutes.
Okay, so I'll be short. We had some results on transcranial evocative potentials, a lot of significant differences in peaks and troughs for a strong 1 millivolt stimulation. We had a little bit less significances when stimulating at 10% of RMT, and we had a significance even stimulating under the resting motor threshold. So no sensory feedback at all was responsible for these studies, whereas no results were present for sham. Differently, we had no plasticity effects on transcranial evocative potentials, showing possibly that corticomuscular and corticocortical circuits behave in a different way. I want just to show you some evidence that even phase synchronicity of Mu-alpha oscillation determines efficacy of interhemispheric communication between motor cortices. Basically, this is a very well-known experiment in TMS. The short interval interhemispheric inhibition happens when you have a conditioning pulse on the left M1 and a test pulse at short distance on the right M1. And the interstimulus interval is between, if the interstimulus interval is between 6 and 12 milliseconds, we have an inhibition of the MEPs in the test M1 and in the test, in the contralateral test hand. This is known as slHl, and it's a measure of effective interhemispheric connectivity. We thought to replicate the slHl experiment, looking at the mutual state of the two motor cortices, and we were looking at some kind of very rough measure when the two motor cortices were both in the positive state, positive, negative, negative, positive, and negative, negative, to see if some kind of communication could facilitate the effect. So these were the states we were focusing on: positive, positive for yours on the left and right M1, negative, positive, positive, negative, negative, negative. And actually, we found that the largest slHl was in the negative state, with the idea that if the two cortices were communicating and were inhibiting to each other, and the slHl measure was enhanced. In general, in-phase measures were showing a higher slHl than out-of-phase measures, showing somehow that the two motor cortex were communicating, and this was considered a nice application of neural communication through coherence. Moving from this state of very elementary communication between the two cortices, the final question is which is the proper activity to close the loop on? And what about online brain network modulation? This is way more complex, and we are working with inverse and forward problems to forward solutions to reach another level of claim and efficacy of such approaches. So we are online reconstructing the activity from the cortical source extraction and trying to trigger the TMS on the basis of source activity. The final aim is of course, online analysis and modulation of brain networks. The idea is to find a network pathology and modulate the network online in a personalized fashion in order to bring it back to a healthy state. Thank you for your attention.
Thank you very much, Paolo. Very, very, very interesting presentation. I must confess, to me, this looks a bit like sci-fi, really. Like, no, really. Let me check if there are questions from the audience. My first question would be, anyway, so because I can really, so the applications of this in rehabilitation, what I mean, how would you use this?
For instance, there is evidence that the mu-alpha rhythm is detectable in the damaged motor cortex in stroke patients as well. And the idea is that a closed loop intervention for this kind of patient can be more effective than open loop. There are different approaches for stroke, for instance. You can either enhance the activity in the damaged motor cortex, or try to limit the activity, the maladaptive activity in the intact motor cortex. Both can be done closed loop, and we have first evidences that this is more effective. In the case of depressed patients, the idea is to fix the imbalance in mostly in alpha and theta oscillations between right and left hemisphere. And again, this can be done, we believe this can be done more effectively with a closed loop approach.
But can you also use these sort of approaches to like improve brain performances? Like that's what I thought about sci-fi. Like, okay. Can you?
So we are about to submit this paper where we were stimulating dorsomedial prefrontal cortex on the basis of source reconstructed activity by means of beamforming, which allowed to reconstruct the oscillation exclusively from the region of interest, saving time, because the key of this kind of approach is to finish your computations in 2-3 milliseconds. And we found evidence that the closed loop approach provided for better performance in working memory during the working memory task. So it does not only affect physiology, it does affect behavior as well.
Wow, fascinating.
This is just the beginning to my assessment.
Fascinating. We have a couple of questions from Andreas. Andreas, you wanna?
Great work, and of course in the direction which is going back to nature very much. Motivation and reward is of course essential, and closed loop stimulation is what we do in social interaction, and probably the most instructive example is what the mother does to a baby, the interaction between the facial expressions, which needs the fast decoding and the reaction. So it's really nice work. Really nice to see it. But did you try to include that? Because you use a very simple paradigm, in the sense you have a single stimulus in a very focal example, but the brain is usually, as you rightly pointed at the end, is a network. One way of introducing that, even in the simple example, to make the study much more, to be able to analyze in more detail, is to include motivation and reward. Did you had any of that? So if you have long experiments, the subjects are very bored, and of course what you see is not the natural state of the system. If you give them some kind of task which would depend on that, and you pay them, the results might be even more exciting.
I understand the point. It's a very good point, and of course, these experiments right now were mostly just resting state for the patient, in theory. So I see two points in your question. One is what happens during the task, and the second one is what happens to brain networks. So first question is first answer is at least during the working memory task, this improved with closed loop stimulation, but it was not part of this presentation. I imagine that a motivated subject could perform even better than a bored resting subject. And about the second question, maybe we can discuss further. But yes, that's a crucial point. After finding a clear result coming out from a local single cortical source, we found difficulties. For instance, to calculate network connectivity online is basically a contradiction in terms. So there are formal and to some extent philosophical difficulties in defining what an instantaneous brain state is.
It might not even be necessary.
Sorry?
It may not be even necessary. I think one of the problems with pathology is that you go out of your normal state, and that's why neurofeedback is so exciting. Neurofeedback state just excites the brain to do something which is natural. So if you manage to know which way to nudge it, you don't need to know what the networks are doing. You just got to push the brain into something which is naturally the more. In my view, the major clinical application of this is not going to be the effect during neurofeedback or closed loop stimulation, but during sleep afterwards. That's where most of the improvements take place. So as long as you nudge the brain away from pathology and addiction, for example, it's just being trapped into an unnatural attractor. So if you manage to nudge it in some way, and that's where your experiments are very important, because you have a simple stimulation and you can actually study how this nudging might take place, then everything would be okay. You don't need to go to the networks then.
Okay, thank you. Interesting.
Okay, thank you very much. If there are no further questions, we can take a small break, maybe 10 minutes, and be back. Paolo, thank you very much again. It was very, 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 very interesting. Thank you.